this lesson is pulling together everything else that we've talked about this week. So we've really focused on factoring, but this tells us why. Why do we factor? Well, because what we're trying to do is we're trying to solve a quadratic equation. Remember, quadratic just meaning that it's x to the second power. And I'm going to show you what that means. So we're dealing with a polynomial equation, and we've already talked about the fact that the degree of the polynomial can tell us how many solutions to expect. So here the degree is 1 because it's z to the first, which means there should be one solution. This would be linear, so something with a degree of 1 is linear. A degree of 2 is called a quadratic, and that's where we're going to put our focus today. But we can expect up to 2 solutions. A degree of 4, actually, let me rephrase that. We can expect 2 solutions. They're not always real solutions. Here I have a degree of 4, and so I can expect 4 solutions. Again, they're not always going to be real solutions. So looking at our first polynomial equation here, and this is, again, it's a quadratic because it's to the second power. And this is a graph of the quadratic, so I'm not going to show you how to graph in this particular course, but if you graphed it, it would look like this. And I want you to notice that it's crossing the x-axis at -4 and at +5. So when I graph it, the parabola, which is the U shape of my quadratic, crosses the x-axis at -4 and +5, which means that if I plug -4 into the function, I get 0, so -4, 0, meaning I plug in -4, 0 comes out, and I'll show you that right here. Plug in -4, 0 comes out. Same thing here, this is 5, 0, which means I plug in 5 for x and get a y value of 0. Now, graphing is tedious, and it's not the way that I want to solve a quadratic. So instead I'm going to solve by factoring. So let's take a look at that same equation, and here's the graph much smaller so that it would fit. If I factored this, I'd be looking for numbers that multiplied to 20 that subtracted to -1, and I would have said, well, that must be -5 and +4. Notice here I put x minus 5 and x plus 4. But over here, remember this was -4 and this was +5. So why are the values a different sign? Well, it's because of the zero product property. The zero product property tells us that if we have 2 terms or 2 factors that multiply to 0, because that's what I'm doing, is finding where does this function equal 0, that either this first value, x minus 5, must be equal to 0, or x plus 4 must be equal to 0. So in order to find what those values must be, I set x minus 5 equal to 0 and solve, and that gives me x equals 5. Notice that matches up. Or I take my second binomial and set it equal to 0, which gives me x equals -4, which also matches up. So the solutions to my equation are 5 and -4. -4 and 5. So the same solutions whether I graphed or whether I factored. But that's all using the zero product property. And we use this whenever we're done factoring and we're setting this equal to 0 to find the zeros of the function. We're going to go through some of these questions together, and particularly on the first one, there is more than one way to solve this. We're going to focus on factoring, so later down the road, the last week of class, we'll talk about the square root method. But for now, we're going to stick with factoring. So if I factor, again, I'm using my shortcuts or my cheat sheet that says here are the steps. And the first step is always, always, always take out a GCF. So if I take out a 9, that leaves me with x squared minus 9, and it's still equal to 0. We always want it equal to 0 so that we can find the zeros. Then I look at the remaining binomial that has 2 terms, and they happen to both be perfect squares. The square root is x and the square root is 3. And so the difference of squares pattern says add them and subtract them. Now before, this would have been my last step. I would have just factored, but they want me to solve. Whenever they want me to solve, they want what values of x could I plug in to make this product 0. So using the zero product property, I'm going to take anything that has an x and set it equal to 0. So x plus 3 equals 0, and solve to get -3. And yes, feel free to do that work in your head. X minus 3 equals 0, and solve to get x equals +3. And typically I would write my solution as -3 and +3, or you might also see it written as x equals ±3. Either is correct. My second example is very similar. I only have 2 terms, but notice on this one, my second term also has an x, which means my GCF is actually 5x. So I'm going to take 5x to the front, which leaves me with x minus 5. And on my first example, I did not have to set 9 equal to 0 because there was no x involved. But on this one, I do have to set 5x equal to 0 because there is an x. And when I divide by 5, I get 0. And then x minus 5 equals 0, which leaves me with an answer of 5, which means my 2 solutions are 0 and 5. And again, I'm just writing those in the set brackets. You can always check your work. Plug a 0 back in for x and see if you get 0. Plug a 5 back in for x and see if you get 0. For my next example, we can see that it's a little bit different because I don't have it equal to 0. I really need it to be equal to 0. So I'm going to add 36 to each side of the equal sign. And when I do that, I get x squared minus 12x plus 36, and on the other side, I get 0. So whenever you have something that is not equal to 0, that's what you're going to do. Now I'm looking for numbers that multiply to 36, that add to -12. This happens to be a perfect square trinomial pattern. So this is actually x minus 6 quantity squared. Or if you have it written as x minus 6 times x minus 6, that's fine too. Notice that this is the same twice. So if I set x minus 6 equal to 0, I know that I'm going to end up with x equals 6, and I don't have to set it equal to 0 twice. I just know that that's going to be my answer, and of course I would write it in the set brackets. Now, I know that we're not learning how to graph in this course, but we already talked before about zeros being where it crosses the x-axis. So if you had a question like this, you would have a parabola that went down and touched at 6 and then turned around and went back up. So that's what it would look like when you have the same answer twice. For my last example here, notice I have x to the third. So yes, this is not technically a quadratic, but we can solve it like we do the quadratic. So I'm going to start by taking out a 3x because it's very clear that each of these have a 3x as a factor. So 3x out front, and then x squared minus 3x minus 24, nope, 28, and equals 0. And now I'm looking for numbers that multiply to 28, that subtract to 3. So I'm going to use x minus 7 and x plus 4. Then I'm going to set each of these equal to 0. So 3x equals 0 gives me an answer of 0. X minus 7 equals 0 gives me an answer of 7. And x plus 4 equals 0 gives me an answer of -4. And I would write those all together, typically least to greatest, but I'm not sure it matters all that much. This is a 4-term, so factoring by grouping question. So I'm going to split it right here. Keep in mind there's a minus. The GCF of my first 2 terms is x squared, which leaves me with x plus 3. The GCF of my second 2 terms is minus 4, which leaves me with x plus 3. And remember, my common factor is x plus 3, so that goes out front. When I divide by x plus 3, I get x squared. And divide by x plus 3, I get minus 4. This one can be factored further because it's a difference of squares pattern. I'm going to keep the x plus 3 out front, but this factors into x plus 2, x minus 2. I set each of those equal to 0. Again, feel free to do the work in your head. I get negative 3. I get negative 2. And I get positive 2. I would write those negative 3, negative 2, 2. This next example is almost exactly the same, but did you notice the negatives on the 4 and the 12 turned into positives? So let's see how that would change things. I'm still going to factor, and I'm still going to end up with x squared and x plus 3. Here I'm going to end up with a plus 4 instead, but still x plus 3. And I would take out my common factor of x plus 3, and that would leave me with x squared plus 4 instead. And the reason this one's different is because this cannot be factored further. This is not a difference of squares pattern. So I would set x plus 3 equal to 0, which would of course give me negative 3. But if I set x squared plus 4 equal to 0, I would have to get that 4 to the opposite side, and then I would have to take the square root of both of those, and the square root of x squared is x, and the square root of a negative, until we talk about i's, the imaginary numbers, for now this is not going to work. So the actual answer here is plus or minus 2i, but all you need to know for now is that this would not give me a real solution, so no real solution. We will learn all about the imaginary numbers and the square root method later on. Go ahead and try these two, and then press play to see how you did. My first example, I would factor this into x minus 7, x plus 6. And that would give me solutions by setting them equal to 0 of 7 and negative 6. Again, I would write them together. Negative 6 and 7. My next example, I would start by getting the 45 to the opposite side. Because you don't know the square root method yet, if you know the square root method, feel free to do it that way. But for us, because we're solving by factoring, I'm going to go ahead and move the 45 over, take out my GCF of 5, which gives me x squared minus 9, and then factor that into x plus 3, x minus 3, which gives me a solution of both negative 3 and positive 3 by setting those both equal to 0.